Okay, example 4. Beam is loaded as shown here, and assume that P, W are the two loads applied on it, and you have L1, L2, EI, those are all given. Determine the reaction forces at B, C, and D. Okay, this time in this example, we're not dealing with a cantilever beam. This is a simply supported beam, overhanging beam. Okay, so the key of this problem will be step 1. So how do we simplify the case? Let's see step 1. Right, step 1 said that we need to remove the redundant restraint and replace it by a reaction force, right? But first of all, we need to identify which one is the redundant restraint. Okay, in this case, of course, you can consider section CD as the simply supported part, and B is a redundant restraint on the overhanging part of this beam. You can also consider BD as the simply supported beam, and C is a redundant restraint on the span of the simply supported beam. Okay, you can do either selection, but I will tell you the option 1 is far more complicated than the second option. So we'll adopt the second option, right, considering BD as the simply supported section, and C is a redundant restraint on the span of the simply supported part. Okay, this is our selection. You can try to consider CD as the simply supported part, and you can do your calculations by yourself. Okay, tell me the result. So I will do the second option. Okay, I will consider BD as a simply supported part. Okay, in that way, we just simplify it as BD is simply supported beam. Then we consider C is a redundant restraint on the span and the middle span. Actually, we can just remove it and replace it using a CY. Okay, and then the concentrated load P at point A. Okay, this AB is the overhanging section on this simply supported. It's an extension of the simply supported BD. Okay, we dealt with this type of situation before in the superposition method for combined beams. Remember how did we deal with this type of situation? Since we're not calculating deflection of any point on AB, so we can actually simply cut it off. We cut AB off, and all of these effects of P on AB on this simply supported part can be concentrated, can be simplified into or represented by a M, by a concentrated bending moment M at point B, and the value of M equals P by L1, right? L1 here. Okay, then this is the beam after simplification. We got a simply supported beam BD, which is loaded by a distributed load W, by a concentrated bending moment M, and a redundant CY. Okay, we have 3 external forces. Okay. Then that is step 2. We split it into simpler parts. Since we have 3 external loading, we just split it into 3 beams. Okay, the beam 1, beam 2, beam 3 will be all simply supported beams subjected to W, CY, and M respectively. So here we got beam 1, subjected to W, beam 2 subjected to CY, and beam 3 subjected to the concentrated M at B. Okay, so we're calculating the deflections at the middle span. Here you get delta C1, delta C2, and delta C3. Okay, we got these 3 components. Then we can analyze the compatibility conditions in terms of these 3 deflection components. Then in step 3, we just analyze these 3 beams one by one. So let's look at beam 1 first. The beam 1 is a simply supported beam BD subjected to distributed load W. So the delta C1 at the middle span can be calculated by an equation. We can select it from here. So the equation will be 11. Okay, equation 11. This is the maximum value in this case. Okay, the C1 would be 5W L to the 4th over 384 EI. Okay, here the L equals, actually, look at here. We have 2 L2s, right? L equals L2 plus L2. That is 12 meter. Then here will be expanded 5 times 60 kilonewton per meter by 12 to the 4th over 384 times 200,000. Then you will get 0.081 meter. Since we didn't consider science, but you need to keep in mind that this will be a downward deflection. Okay, this is a downward deflection, and we did this calculation based on equation 11. Okay, then will be beam 2. Beam 2 is here. Beam 2 is a simply supported beam subjected to concentrated CY applied at the middle span. Okay, and here this is the delta C2 can be calculated. Again, we need to select a equation, and this will be here. Right? Simply supported beam subjected to concentrated middle span load P. And again, this is the maximum deflection. We just use equation 2. Okay, so the delta C2 will be calculated by PL cube over 48 EI. Again, here the L is the same as there. It's L equals 12 meter. So this equation will be expanded. The P is CY times 12 cube over 48 times 200,000, and this will be CY over 5556. But it's note that this is the upward deflection. Okay, as shown here, this is the upward deflection, and we did this calculation based on equation 2. Then beam 3. Beam 3 is the simply supported beam subjected to a concentrated load bending moment M at one of the end, at end B. Okay, the equation will be here. So we will select the equation 9. Okay, since this time the middle span will not be the maximum deflection, we need to use this equation. Okay, the delta C3 equals mx over 6L by EI times 2L square minus 3LX plus x square. Okay, this is our equation 9. Here we need to analyze those values, right, in this equation. Right? First of all, the m equals, as we analyzed here, the m equals p times L1. That is 120 by 3. 120 by 3, that is 360 kilonewton meter. And the x in this equation equals this L2, since it's middle span, so this is L2 or 6 meter. And the L, in this case again, it's 12 meter. Okay, just using these numbers, we can calculate the delta C3. So it will be 360 by 6 over 6 times 12 times 200,000 by 2 times 12 square minus 3 times 12 times 6 plus 6 square. Okay, and here we will get 0.0162 meter. Okay, then we're done with step 3. Okay, in step 4, we will analyze the compatibility. At point C. Right, so what is the compatibility condition here? Since we have a roller support at point C, so obviously the compatibility equation at point C will be the sum of the delta C equals 0. Okay. In step 3, we have determined the three components of this delta C, delta C1, C2, and C3. Okay, and we denoted their directions. And the delta C3 is a downward deflection, delta C2 is upward deflection, and the delta C3 is another upward deflection. Okay, so the equation, the compatibility equation, can be written as delta C1 plus delta C2 minus delta C2 minus delta C3 equals 0. Okay, since delta C2 and C3 have the same sign, the same direction. Okay, then we will substitute the numbers in this equation. You get a 0.081 minus Cy over 5556 minus 0.0162 equals 0. So from here, you can calculate that the Cy equals 360 kilonewton. Okay, so now we have determined the reaction force at Cy. Okay, since in this equation we're requested to determine the reaction forces at BCD. So if we determined C y, then what are by and dy? Since you didn't add any force along x direction, so the reaction force dx will equal 0. So you have only by, cy, and dy. These are three reaction forces you need to determine. We already determined cy, so the rest will be by and dy. Okay. So how to determine by and dy? This will be actually a problem of statics, not mechanics of materials. Okay, let's see that. So how to determine by and dy. So you can select a point, and then around which the sum of bending moment equals 0. Right? Let's see if we sum md equals 0. You need to go back to the original figure. Okay, let's summarize it here. You have a dy, you have by, you have cy, and you have a distributed load W, and you have a P here. Okay, if we calculate the sum of MD equals 0, you have 4 components, and the first component will be P by the overall L A D. Right, so here is A, B, C, D. Okay, you have a P by AD plus W by BD by CD, right? Then minus BY times BD minus CY times CD equals 0, right? Then here you will have, actually P is 120 times the sum of the 3 things will be 3 plus 6 plus 6 will be 15 plus the W is 60. Okay, the 60 times BD is 12, CD is 6, then minus BY is unknown, times BD is 12, minus CY is 360 times 6, right, equals 0. So from here, we can get that the BY equals 330 kilonewton. Okay, this is our second reaction forces that solved from here, from this equation based on statics. Right, the last one, the dy would be just as simple as sum Fy equals 0. Since you already know P, W, and By, Cy, so only unknown is dy. So okay, you can solve that one. I will not give details since this is simple enough. So the dy can be solved as 150 kilonewton. Okay, this is the third reaction force that we determined. Okay, to sum up, we just solved all of these reaction forces at B, C, D, and the result is B here, C here, and D here.